Welcome back to STEM Online Academy. My name is Jason Masterakos, for those of you who don't know. Okay. And what I want to look at today is a very interesting topic when it comes to calculus, which I think you will find engaging and fun, right? And that is tangent lines are not actually lines. I'm going to explain. Okay. So if you think a tangent line is just a line, right? Uh, Touching a curve, then you're actually missing the entire point of calculus. Okay. So here are some questions I want you to think about. Right? Think about some of these questions. Okay. Why does calculus replace a curve with a line? What's the geometric significance of that? Okay. What does local actually mean? Okay. So these are the two questions. So what does local actually mean as a from a definition perspective? Okay. What is the derivative? Okay, as a microscope and not just a slope, right? And when is a tangent line a good approximation, right? And when does it when does it lie? Okay. Um, and finally, then another thought-provoking question that I want you, the audience, to think about is why does linearization make abstract mathematics actually, you know, manageable? Okay, so these are questions I'm going to be talking about in the video. Okay. So if you look at question one, why does calculus replace a curve with a line? Right. So what do I mean by that? What does the question mean? Right? Take a moment to think about it. Why does calculus replace a curve with a line? Because calculus is about instantaneous rates of change, right? You should know what that means. What is instantaneous, right? So finding the rate at which something goes at a specific point, right? That's what calculus aims to study mainly, right? Instantaneous rates of change. Okay. So, and we measure that instantaneous rate of change by taking the first derivative of a function mathematically, right? We take the first derivative, and from that first derivative, we get a new equation, right? We can then model that equation geometrically, right? And the first derivative is related to the slope of the function that we're dealing with. Okay, so if you take the first derivative at a specific point, right, at a specific coordinate x, okay, we're able to pop out the slope. Okay, and that slope of the line, it's a slope of a line, is the tangent line. Okay, right. So that's one of the questions you want to talk. Another question that we should answer was what does local actually mean? What is local? What does local mean? Okay. Uh, I don't mean your local grocery store. I don't mean that. I mean local math in mathematical terms. Okay. So when it comes to locality, okay, we mean zooming in at a specific point, right? Just really zooming in and figuring out the properties of whatever function we're dealing with. Okay. So let me pull up the whiteboard here. I'm going to have the whiteboard on the second screen. Okay. All right. So give me a moment here. Yeah. We're going to have over here, if you can see it. Okay. I'm going to out zoom first screen a little bit. Okay. And then we got this guy over here. Right. If you look on the second screen, right, you'll notice that I have some curve. Okay. So let's look at the curve in more detail. Okay, just one sec. For some reason, just give me a sec why this is not. Just give me a moment, guys. Okay, just one second. If this guy is going to work. Capture. Chrome. There it is. There it is. Yes. Okay, so as you can see, we have our curve here, our original function. It's some type of either cubic function, may also be Let me see. So then we have a sine. It doesn't matter. It could be a cubic function, it could be a sine function. I sort of, that's what I meant by local. Local means we zoom in on the function uh, by a lot, okay, at a specific point. All right. So I can't see the entire function. I just modeled it with the simulation. So it's some function y equals f of x. We don't need to know the exact function. Okay. Now, if if you notice right here, right on the second screen, the blue curve represents the function y equals f of x. Okay. Right? I hope you guys can see that. Right? So y equals f of x. All right. Now, the tangent line is that red dotted line, the local linear model, right? Now, a tangent line hits at exactly one point on a curve. Okay, that's what a tangent line is, and that is rate measuring the instantaneous rate of change. Okay, so exactly one point on the curve is touched there. Okay, with that red dotted line. Okay, and what you can see is I'm taking a rectangular segment here of the point in which the tangent line hits exactly that point. Okay, so on the first graph here on the left, right, I've done that. I've zoomed in and I'm showing you exactly the behavior, what's happening at some coordinate x naught comma f of x naught. Okay. Now that point there, you may be asking, looks cool if you're interested in tangent lines, but the main point is when it comes to local, the definition of local. So we zoom in very much in the graph, like we really magnify the graph, right, at a specific point, right? And that's what locality is, okay? So if you look on the second graph here, right, we have the tangent line by itself, okay? This is where I really magnified. I've magnified the tangent line approximation, okay? Now, from the first graph, I had the curve, right? So that blue curve, okay? And we had a tangent line there. And I just got rid of the blue curve for the second graph, and I just have the regular tangent line, right? Okay, so you can see the tangent line there, all right, and that is point of locality. That's the geometric area of locality that we're looking at here when it comes to what local means. Okay, that's all local means when it comes to mathematical definition. All right. Okay. So, oh, by the way, if you have any questions at all about any concepts I am discussing, or any disagreements, or anything that you would like me to discuss more on, please put it in the chat when I've uploaded the video, obviously, right? Because this is not a live video. Okay. So you can see here, right, that my line is slightly there, and we're looking at uh, the local behavior. Okay. Now, the third question is, why is the derivative a microscope and not just a slope? Hmm? Why is derivative a microscope and not just a slope? Now, this is conceptually a little bit tricky to understand because all of you have learned that finding the first derivative gives you the slope. Not precisely, though. Finding the first derivative at a specific point, yes, to be defined at a specific coordinate, gives you the slope. Okay, at the specific point gives you the slope. Now, the derivative alone, right, is giving you um, is giving you uh, the function is giving you the function primed, right? Okay, if that makes sense. We take the original function as a function of x, and we get a derivative of that first derivative in terms of x with respect to x. We'll spit out a function of x, and that function, okay, is going to, like, in terms of geometric wise, right? With geometrically, what it means is that we have some sort of, you know, area, not area, location of where we want to, you know, define the slope. Okay, so that's what my global nonlinear curve and local model is showing here, right? It's showing exactly that. It's showing that rectangular region there, right? is where we're going to be focused on defining the slope, right? That rectangular region with the circular dot is going to tell us exactly the slope at that point. Once we have the slope on the point and we calculate it mathematically, okay? All right. Now, does that make sense? Now, if you actually I want to bring up something that's very important about myself, which is very true. Okay. When it came to mathematical concepts and uh, problem solving, at one point in my life, right, from grade 7 to 9, I was not a good student. Okay. I was struggling with mathematics heavily, like really bad, really badly. And it wasn't because of the fact that I had some sort of, like I'm not meant to do math, or I have some problem learning, or not mathematical genius or some sort. Um, but in reality, it was just that I wasn't taught a way of thinking. Okay, mathematics is a way of thinking. Okay, it's not regurgitation. It's not formulas. It's not any of that nonsense that they teach you in school. Right? It's about reasoning. Okay, that's what mathematics is. It's about reasoning, being able to reason and communicate your thoughts effectively. These two things have to be in synchronicity. Okay, if they're not, it's mathematically you'll always be wrong. Okay, so from my experience, right, as I said, I wasn't a good student when I was younger, until I had um, two teachers, one teacher in the end of grade 9 and one in grade 10, and they both taught me this. They taught me that um, you need to develop an immense problem solving ability, right? And what I mean problem solving ability, I don't mean doing rote regurgitation type problems. Okay, I'm like I, and that's the problem. That's the deceiving thing about mathematics, especially if you have a bad teacher. They'll give you, for instance, question one for homework is x plus one. Question two will be x plus two. Question three, x squared plus three. Right? Those problems anyone can do. Right? Even anyone can do those problems. I'm not talking about that. I'm talking about the problem solving part of it. Okay. And I'm sure a lot of you can relate. It's like, oh, I do the homework. Homework is so easy. How come on the test I'm having trouble? Because you haven't practiced problem solving. And you only way to do problem solving is to have a system that works. My system, you can use my system, right? Is visualize. Step one is to visualize what's going on. Okay. Geometrically or physically in the problem of the system. Step two is to model. What I mean model, I mean to create a semantic map of what you know and don't know and your plan of attack for the problem. It's very important. Step three, you want to be able to execute. The execution part is probably the easiest. You just um, algebraically from step one and step two, plug and chugging everything. Okay. And then step four is proving slash verifying. Okay. This system is very handy for university students. Okay, and it's helped. It's really helped me. Right, I developed it myself. I found the technique that works for me. I'm not saying it will work for you, but I'm saying it works for me. And you need to find the system that works for you. Okay, right, and um, don't use what's it called, AI to do it for you. Right, you need to. That's the problem. People use AI and they for math, and they're noticing that they're having major negative effects from it. Okay, because that's not what it's for, right? In the end of the day, right? When you go to that test, it is you writing the test, not the AI, right? And you need to have independent critical thinking skills that will take you way beyond what AI can do. AI can create a lesson plan for you to maybe practice some problems, right? But when it comes to learning the ability to think, no, it's nonsense. It's not going to help you. Okay, all right. So again, back to what I'm saying about me, right? I was able to um, go through high school using the technique that I discovered, right? for myself. Grade 11 and 12, outstanding results. Okay. Went to university, Carleton University, studied mathematics and physics. Got a double honors degree in both. Ended up with a 3.85 GPA. And so I know what works. I know where this can take you. Okay. All right. And I want to be able to share my gift with the rest of you, right? Making hopefully mathematics and advanced mathematics and physics more attainable um, for students, right? For students and independent learners who just want to learn math too. Okay, right? So, and that's what STEM Align is about, right? STEM Align is exactly that, right? To we want to be able to uplift the individual, right? Problem solving in that approach, right? Not to depend on AI, okay? Right? You're the thinker. The technology is just a tool, okay? So back to it, all right? So I was discussing these guys here to write down my questions. Let me look at my questions, right? I always forget what it was. Another question I wanted to discuss. I discussed like three of them. Those three thought-provoking questions. When is a tangent line a good approximation, and when does it lie? So a tangent line would be a good approximation, right? When is it a good approximation? Think about it. When is the tangent line going to be a good approximation? Well, if you look at the equation of a tangent line, right? And I mean the point slope form, right? Y minus y0, right? Equals the slope times x minus x0, right? Taking that equation and then uh, finding an approximation, right? Uh, by solving for y, obviously. So you rearrange the point slope form, put it in terms of y, okay? That will give you a good approximation for any tangent line, okay? At x equals the specific coordinate in which your tangent line intersects for the instantaneous rate of change, okay? And then finally, why does linearization make abstract mathematics more manageable? Well, it makes it more manageable because first off, you're putting it in terms of a geometric understanding. Quite often, abstract mathematics um, intuitively is hard to picture. I find with even when I was studying it in university, it's hard to picture it. Okay? And it's even harder for students to picture it, right? So having some sort of geometric description in your mind will really help understand the topic conceptually, right? So you want to be able to do that, right? And that's where my and here's another thing. That's where my systems technique comes involved, right? Because the first step one is to visualize. See how all this makes sense? How mathematically I've been able to find the ultimate system. Okay. And I want you to do the same. Okay. Or you preferably use my system, it would be great. But you'll see the benefits. Do we have any other questions? Okay. So I think that is it for today's video. Again, I want to mention before I go some things, right? My systems technique that I mentioned about. If you don't know what it is, you don't understand it, please download the free PDF in the link below. Okay. Actually, everything will be in the link below. Okay. My PDF will be in the link. Okay. And also, I have, I have, I have two books. Um, depends what it is. If you have trouble with the systems technique and you have trouble, I haven't discussed in this video, but you have trouble logically solving um, mathematical problems, you may want to check out my book Axioms. It's a good resource. It introduces you exactly to reasoning, okay, before you actually tackle courses like analysis, less calculus, or anything else of that nature, right? Or any other math course. Okay, because it teaches you not only to think logically, but the systems and theorems that you need to know in order to prove or disprove something. Okay, so if you need, and it's a very good, and a bit challenging introduction to reason. Okay, so you may want to check that out. Okay, and finally, um, not finally, now if you're an advanced student who wants a real challenge when it comes to just calculus in general, you may want to check my mathematical methods book, Advanced Integration Techniques. Okay, it involves tackling uh, hard to open-ended integral problems. This is not advised for the majority of you. It is a very hard book. Okay, but if you enjoy that challenge and you're an undergraduate student, you want to test your ingenuity, please get that book. And finally, um, if you prefer, right, if you prefer not having the resources, and if you prefer, and obviously, uh, uh, if AI is not helping you understand the concepts, because more likely it isn't, then you need someone, and you need someone who can actually give you face-to-face interaction, understand your needs, understand what it is that you're struggling with, tailoring things to the way that you want um, your learning plan, and so forth. I offer coaching when it comes to calculus and physics as well, right? And I'm going to help you get through uh, those specifically hard midterms and hard exam style questions. Okay. All right. So again, it's always a pleasure, guys. Um, Write anything in the chat if you need. I'm going to try to do 2 to maybe 3 times this week. I've been very busy, but don't worry. We're going to talk about more interesting concepts. And yes, uh, yeah, more interesting concepts coming up and possibly problems. I'm not doing as many problems as I did before. I want to show you and like stem lines system for solving problems as opposed to doing the problem, right? I want to now coach you guys through with my systems technique and how it can help you benefit. Okay. Have a great weekend, guys. See you next time.